We are going to finish up the sample final number 1 for UCI Math 2A. We left off on number 14. This is a derivative problem. This should be easy points. Derivatives are easy. All right, so first one, dy dt for y is this whole guy. We just use the power rule for the first two terms, and derivative of e is just e, very easy. So dy dt is equal to, this is the same thing as t to the negative half, so it'll be negative half t to the minus 2/3 power plus 5 plus 3 e to t, as simple as that. Okay, now next, f prime of 4 for f of x is this guy. Okay, so let's just find f prime first. F prime of x is, here we need the chain rule. The derivative of square root is 1 over 2 square root 9 plus 4x times the derivative inside of the square root, that's just 4. Okay, and we evaluate this guy at x is equal to 4. So what do we get? We get 4 over 2 square root of, that'll be 9 plus 16, which is 25. So that is equal to, so this we can already simplify to 2 on top, so it'll be 2 over 5. All right, next, f prime for f of x is this guy. We need the chain rule. F prime of x is, we go outside in. So derivative of sine is cosine. Everything on the inside remains the same. Now we differentiate the inside. We need the product rule. It'll be first, d second, derivative arctan is 1 over 1 plus x squared. So I multiplied the x with it, right? Plus second, d first, derivative of x is just 1. And that's your answer. As simple as that, chain rule. Here we need product rule and chain rule for this guy. H of r is this guy. We need h prime of r. H prime of r, so once again, we do product rule first. D second, derivative of log is 1 over the argument. And then we need chain rule times derivative of inside the log, which is 3. Because this derivative of 3r. All right, plus second, d first, derivative of r is just 1. So we can simplify. This becomes 1 plus log 3r. All right. Now, last one on this page. See how easy these are, how quickly I'm going about them. dy dx is this guy. Here it's x to the x power. We need to use logarithmic differentiation. So we log both sides. ln y is ln of x to the tangent x power. Remember, we can bring out the power when it's inside the log. So we can write it as, tangent x to the, tangent x times ln x. All right, so now we differentiate both sides. It's 1 over y, dy, dx is, derivative of tangent is, let me write it a little better. So here we have tangent x times log x, okay? So here we need product rule. First, d second plus second, d first. I think this is the third time I said this already in this video. Right, so first would be tangent x. D second derivative of log is 1 over x. Plus second, d first derivative of tangent is secant squared. All right, so we solve for dy dx. As simple as that. Dy dx is, so we have all this over here, which we can write as tangent x over x plus secant squared of x log of x times log of x, all multiplied by y. What is y? Y is just x to the tangent x. So this is your answer right there. Okay, as simple as that. Now let's move on to the curve sketching problem that's very involved and algebra heavy. Okay, algebra as in tedious math heavy. I think it's totally unnecessary, but let's do it. It's not too bad. Let's find the domain of f for this guy. What's the domain? Well, we'll never divide by 0 because x squared, that's always positive. All right, and we're adding 1 to it. So the smallest value that x squared can be is 0 when x is 0. But we're adding 1, so we're never going to divide by a 0. So we have the domain is all real x, or all real numbers, whatever you want to say, okay? Okay, find the x and y intercepts. For the x-intercept, how do we do that? That's where it crosses the x-axis. So we set y to be equal to 0. Okay, so when y is equal to 0, that is when x is negative 1. All right? How about the y-intercept? Instead of setting the y as 0, we set the x as 0. So we just plug in x as 0. We get 1. All right, so those are the two intercepts. Determine if f is even, odd, or periodic, or neither. I think this is missing because it's definitely not periodic. This is a rational function. Is it even if we plug in x as negative x? Do we get the same thing back? At the bottom we do, but at the top we don't. So it's not even. And it's not odd because do we get negative f of x when we plug in f of negative x? We don't. Because again, this one would make it positive. Negative x squared would just be x squared. So, and then inside here, it's also not negative of this guy. So it's not odd either. Remember the test for even, it's if f of negative x is f of x, which is not, and odd if f of negative x is negative f of x, which is not also. So it's neither, and it's not periodic, so it's actually none. All right, so let me write it like that. Okay, it's missing something in the question. All right, find any vertical, horizontal, or slant asymptotes. We said earlier that the domain is all real x, so no vertical asymptotes. How about horizontal asymptote? Well, we can expand the top out to be x squared plus 2x plus 1 over x squared plus 1. We have a horizontal asymptote at y is equal to 1. How do I know that? Well, I could take the limit as x goes to infinity, obviously. But remember, for a rational function, the easy way is we compare the degrees. They are the same. When it's the same, we take the ratio of the leading coefficients, which is just 1 over 1. So y is equal to 1. There's also no slant asymptote. That happens when the degree at the top is less than the degree at the bottom. Okay. Find intervals on which f of x is increasing and on which it is decreasing. That's the first derivative test, okay? So this is the function, okay? So take note of that, because I can't fit it all on screen. I'm going to do the quotient rule to find f prime. So f prime, let me start from here even, is, okay, so I'm going to use this one. I might interchange actually, so you'll see how I do it. Sometimes differentiating this is easier, sometimes differentiating this is easier. And you'll see for the second derivative, it's much, I might mix and match, okay? So for this one, let's do bottom d top. So bottom is x squared plus 1. D top, derivative top, I'm going to use this guy probably. That is 2x plus 2 minus top. So I'm going to use the expanded out form. D bottom, that's just 2x over bottom squared. Okay. That is the first derivative. Let's simplify because we need to set it equal to 0 and find the critical points, okay? Excuse me. So let's expand this whole thing out. Okay, so it'll be 2x cubed plus 2x squared, right? And then plus 2x plus 2 minus parentheses. I'm distributing this 2x to all these now. 2x cubed plus 4x squared plus 2x all over x squared plus 1 squared. So now I see that some terms can be canceled. Which ones? Well, there's this plus 2x cubed, there's this minus 2x cubed, there's this plus 2x, there's this minus 2x. So we are left with what? It looks like 2x squared minus 4x squared, that's minus 2x squared, plus 2 over x squared plus 1 squared. Okay, so now we set this equal to 0. So that happened, excuse me, when we set it equal to 0, that only the top matters, right? Minus 2x squared plus 2 is equal to 0. So we get the solutions that what? X squared, okay, let me just go slowly. I can move this 2 to the other side and then divide by negative 2, so we get x squared is 1. X is plus or minus 1. And actually, I could have factored over here if I had, let me write it like this. 2 times minus 2 times x squared minus 1 over x squared plus 1 quantity squared, like that. Okay, so this, you can hopefully see the solution is x is plus or minus 1. All right, so we do our first derivative test using our critical points. We plug in some huge negative number. Where do I want to plug in here? I definitely don't want to plug in from here. Maybe from here. We plug in some huge negative number. This guy would be positive, this x squared minus 1. This guy is always positive, but this is negative 2 outside, so the sign is negative. You plug in some number between negative 1 and 1, like 0. When it's 0, then this is negative. 2 negatives make a positive, so positive on top, and then positive on bottom, because it's something squared, that's always positive. And then we plug in some huge positive number. The bottom is positive. Again, this guy would be positive, but we have this negative 2, so the sign is negative. So f is increasing from negative 1 to 1, and f is decreasing from negative infinity to negative 1, union 1 to infinity. Okay? That's how we do that one. Find any local max and min values. No, it says values, okay? So we did our first derivative test, so we know that there's a local min at x is negative 1. And there's a local max at x is equal to 1. How do I know that? Derivative goes from negative to positive, so that's minimum, because when the derivative is negative, the function is decreasing, and then derivative is positive, the function increases. Decrease, increase, that's a min. Similarly, positive to negative, it'll be increase, decrease, that's a max, okay? What are the values? When x is negative 1, we plug back into f. Up here, when x is negative 1, we get 0. All right? When x is 1, what do we get? We get 1 plus 1, which is 2. 2 squared is 4 over 2, which is 2. Okay? So we can do it like that, or you can even write it as min. The min point is minus 1, 0. The max is 1, 2. We would write it like that. Okay? So let me box this up here also. Okay? Now let's move on. So I'm going to move to the back, but I might reference this now and again. Actually, I have a copy. It's a lot smaller, though, of the problems here. It's printed on half a page. Let me try to refer. So next is find intervals on which f is concave up and on which it's concave down. So we need to do second derivative, okay? So let me, how should I do this? Well, we have, let me write it here. We got this to be f prime, right? So let me write it once more. F prime is minus 2 x squared minus 1 over x squared plus 1 squared. So I'm just going to expand it because sometimes it's easier to differentiate a whole polynomial and not keep track of all the chain rules. Okay, so let me expand it back to minus 2x squared plus 2 over the bottom. We can expand at x to the 4th plus 2x squared plus 1. Okay, so I'm going to use this to find f double prime. So let me do it from over here now. F double prime is, here's our f prime. We need the quotient rule again, okay? So here I'm going to mix and match, as I said. So I'm going to just do what I think is easier. So bottom, I'm going to use this one, because remember these are equivalent, so I can pick and choose. Bottom d top, I'm going to use this. Derivative of this guy is minus 4x. Minus top, so I'm going to use this guy again. D bottom, I'm going to use this guy. That's 4x cubed plus 4x. All right, all over bottom square. I'm going to use this guy now instead of squaring this guy, because this guy squared is just x squared plus 1 to the 4th. Okay, so that helps with this notation, in my opinion, okay? So now let's clean this up. Let's distribute everything and see if things can cancel. We get a minus 4x to the fifth minus ax cubed minus 4x minus parentheses. Here we get what? Minus 8x to the fifth, right? And then minus 8x cubed plus 8x cubed plus 8x. Hopefully I did that right. All over x squared plus 1 to the fourth. Let me check that I did that right. I did this beforehand. Okay, I think I got the same thing. So we see that these can cancel, and then we can start simplifying, okay? We have minus 4x to the fifth, and then plus 8x to the fifth, so that's 4x to the fifth. All right, we have minus 8x cubed. There's no x cubed over here, so we still have the minus 8x cubed. All right, minus 4x, there's a minus 8x, so minus 12x it becomes. All right, and I counted for all the terms, over x squared plus 1 to the fourth. All right, now I can factor from the top 4x, it looks like, and it becomes x to the fourth minus 2x squared minus 3 over, the bottom stays the same, okay? And then I can factor this guy, that's 4x, so you have to be good at factoring. X squared minus 3, x squared plus 1, all over x squared plus 1 to the fourth, okay? So we can actually cancel 1 power from the bottom, it looks like. So we can finally say, and we can factor this x squared plus 3. So we can finally write 4x times x plus root 3, x minus root 3 over x squared plus 1 to the third power, okay? Now we set this equal to 0. We see that we have critical points that x is 0, negative root 3, and root 3. Okay, so we do our second derivative test here. We plug in some huge negative number. What happens? Okay, so it's a cubed on the bottom, so we got to be careful. Well, actually, it's first, if it's a huge negative number, that guy squared becomes positive. Positive cubed is positive, so I think the bottom will always be positive. So let's look at the top. This would be negative if it's a huge negative number. Negative, negative. So 3 negatives and a positive, so the sign is negative. All right, we plug in some number between negative root 3 and 0. So we can plug in like negative 1. If you don't remember what root 3 is, I think it's like 1.9 or something like that. Even I don't remember. You could do an easy trick where we just plug in something very close to 0, like negative 0.1. Okay? So we just care about the sign. So we can plug in whatever we want, whatever is easiest, okay, to help us determine the sign. So as I said, the bottom is always positive. How about here? It's negative. Plug in that like negative 0.1 here. This would be positive. Over here would be negative. So these two are negative. This one's positive. So the two negatives make a positive. So everything is positive in that. All right. So similarly, we can plug in like 0.1. All right. So this would be positive. This would be positive. This would be negative over here. And then this bottom is positive. So the sign is negative, right? And then we plug in a huge positive number. This will be positive, this will be positive, this will be positive, bottom's positive. Okay, so it's concave up where? Negative root 3 to 0 union root 3 to infinity. And it's concave, let me write it, concave down for negative infinity to negative root 3 union 0 to root 3. Okay. Now we're asked to find points of inflection. That's where the second derivative changes sign. So it's at here, here, and here. So it'll be at minus root 3 comma something, 0 comma something, root 3 comma something. Okay, so what are those somethings? So where is our f? Let me write it once more. F is, let me look it up on my computer real quick, is x plus 1 squared over x squared plus 1. Okay, so we just plug in those values of x. So like when x is 0, that's the easiest one. We get 1 over 2. Okay. Sorry, not 1 over 2. It's just 1 because I'm not adding 1. So sorry about that. So it's 0, 1 because when x is 0, it'll be 1 divided by 1, right? So when x is negative root 3, what do we get? We get negative root 3 plus 1. We can just write it like this, squared over 4. And when x is root 3, we get root 3 plus 1 squared over 4. Those are our points of inflection. All right, now we're asked to sketch f using what we found throughout this problem. Okay, so let's flip. So this is why setup is not good, because I have to flip back and forth. Even on the test, you might have to do this. So we know that there's an x-intercept at negative 1, 0 and a y-intercept at 0, 1. Negative 1, 0, 0, 1. So we know that we have those points, okay? There's a horizontal asymptote at y is equal to 1. So we can draw like a dotted dashed line. So we know that there's going to be an asymptote there. Okay? So f is increasing from negative 1 to 1 and decreasing everywhere else. And we know that there's a min at negative 1, 0, a max at 1, 2. So let's plot those points. Negative 1, 0, 1, 2. Negative 1, 0 we already have. 1, 2 is here. Okay, so this one was which one? The max, I'm guessing. Yeah, and min is over here. All right, so it'll look something like this, right? So we can even kind of sketch it right there already for the min and the max. And you can probably guess that it's connected there. All right, how about points of inflection? Well, this is harder to estimate because you need to know what the value of root 3 is, but we know that there's a point of inflection at 0, 1, so you can just connect it like that because we know it's continuous. It's continuous because that's the first part. Domain is all real x. Okay, so you can see that here it changes concavity. Here it's concave up, and then it's concave down. All right. Excuse me. So we know that it changes concavity again at minus root 3 and positive root 3. So it's going to be like somewhere here, somewhere here. All right. So let's say this is root 3 and this is minus root 3. This is what? Oh, it's minus 1. This is 1. This is 1. This is 2. Something like that. Okay. So we know that it'll change concavity here again. All right. So we have to associate it with this probably, that f is after point 1, after x is 1, it's going to decrease, okay? So after this guy, it's going to decrease, and it's going to change concavity. So right now it's concave down. We need to change it to concave up here, so it might look something like this, okay? And then, there's asymptote, so it never crosses, okay? Similarly, over here, it changes concavity at negative root 3, and then we know that f is decreasing from negative infinity to negative 1. Okay? Did I just say increasing? It's decreasing. Okay? So it's going to decrease when we go this way. So it'll look something like this. Okay? So you can see that it's not a very good sketch, but this is concave down. It changed to concave. Concave up here and changed to concave down. Not exactly at this point. My sketch is not great, but something like that. All right. So this is the sketch of f. So we took into account the intercepts. All right. There's a min and max. We took that into account. And then points of inflection, we also took into account. And then we also used this to help us out to determine how F looks, okay? So this is a very coarse sketch. Not the best sketch, but it gets the job done. And it has all the information that we have, all right? Okay, so this problem in itself took the majority of the time in this video, but that's okay. Hopefully it was helpful. Please like this video if you found it to be helpful, and please subscribe to the channel to also show your support and to look out for more videos like this.